Okay, we're looking at test 3 practice test. To start with, we're identifying the next two terms of a given sequence. Now, we're not going to make this crazy like some of the ones we looked at back in 9.1. You can anticipate this will be either like a common number being added, or a common multiple, or a scaling addition, which we see in the denominator here. Now, the numerators, we know 1, 3, 5, and 7. Okay, next will be a 9, and after that will be an 11, understandably. Now, on the bottom, 5, 11, 19, 29. Well, to me, we can say, okay, we're increasing by 6, then by 8, and then by 10. So that means in the next step, we anticipate increasing by 12. So 29 plus 12 will give us a 41. And then plus 14, which would bring that to 55. So we can do 9 over 41 and 11 over 55. And that would be our answer there. Now, if we just put in, we know realistically 11 over 45, or 11 over 55 is 1/5. So we can go ahead and reduce that if we want. If you don't reduce it, it's no big deal on this one at least. So, because it does demonstrate the pattern. Okay. Number 2, determine whether the series is convergent or divergent. If it's convergent, find its sum. The only thing we can ask for the sum for specifically is going to be a geometric series. So our anticipation is that this will be a geometric series. So in geometric, now it's strictly a matter of finding the common multiple to get from one term to the next. And because some of these fractions may be reduced, it's not always the easiest to tell what's happening. Like from the first to the second term, both numbers got smaller, so it's hard to tell what that multiplier is. But then if we go from the first one to the second term, or the second to the third to the fourth term, 1 times 3 gives us 3, times 3 again gives us 9. So it looks like we're multiplying by 3 in the numerator. On the denominator, 2 to 8 looks like we're multiplying by 4. 8 to 32, still multiplying by 4. So times 3 in the numerator, and times 4 in the denominator. So our ratio is 3/4, and our first term is 2/3. By the way, if we do 2/3 times 3/4, we get 2 times 3 is 6, 3 times 4 is 12, 6 over 12. That reduces to 1/2. So it does fit the pattern. It's just somewhat concealed in that first to second term because that second term is shown reduced rather than the multiplied out term that would be 6 over 12. Okay. Anyway, now first of all, is this or does this converge? Well, according to the geometric series test, if the absolute value of r is less than 1, then yes, it converges. So we know it's geometric. Absolute value of r is less than 1. Check. So it converges. Okay, so we know that. And if it does converge, we want to find the sum. Now our sum is equal to a over 1 minus r. A is the first term of the series, r is the common ratio. And so we already got these two values, so we'll take 2/3 over 1 minus 3/4. Okay, so our sum is going to be 2/3 divided by, and that'll be a 1/4 on the bottom, and so the result is 8/3. So that's our sum. So we know that this does converge, and it converges specifically to a sum of 8/3. All right, 3. Use the integral test to determine the convergence and divergence. Let me Sorry, my keyboard is in the way. Determine the convergence and the divergence of the series. Assume it already meets the necessary criteria. Now, by that we mean there's three things that we had to check to be able to use the integral test, but we don't want to worry about that here. We just want to perform the integral test. And now the integral test says we can create a function f of x that is representative of this series. Okay, so we change our variables from n to x. And if we can integrate this function between these two limits and the integral converges, then that means this series also converges. But if this integral diverges, then that means this series also diverges. So that's what the integral test will tell us. So we want to find the integral from 1 to infinity of x over x squared plus 1 to the 3/2 dx. Now we learned a lot of different integration techniques in chapter 8. I just want to say probably I'm going to keep this to a simple substitution. At the worst, maybe an integration by parts, but the most likely scenario is just going to be a u substitution for this integration. And we saw on the extra credit assignment, it was a u substitution. Here it's a u substitution, and I'm pretty sure that's what I put in the actual exam, is a u substitution. So keep that in mind. We could ask something more difficult here, but in the goal is to make sure we're doing the integral test properly, not this integration properly. Although that's part of it, we don't want to make it overly complex at the same time. So I think anticipating a u substitution here is a reasonable expectation. Now, we can see we have an x squared plus 1 here. Here its derivative appears in the numerator, not quite its derivative, but it's the variables there. U is equal to x squared plus 1. Our derivative is 2x. Now we only have an x times dx. We'll just bring that 2 over. So that means that we have the integral, 1/2 the integral, 1 to infinity, and this will be du over u to the 3/2. Now with the u to the 3/2 in the denominator, let's rewrite that with that in the numerator instead. So that is u to the minus 3/2 du. And we can integrate that using the power rule now. So that is u to the negative 1/2 times 1/2 divided by negative 1/2. It's a little confusing with the numbers there, but we'll get through it. So what happens with our numbers? Well, the 1/2s actually cancel. It is still negative, and then we have 1 over square root of u from 1 to infinity. Oops, sorry, there we go. And now we just plugged u back in, which is x squared plus 1. So we get negative, and then 1 over square root of x squared plus 1 from 1 to infinity. Now if we plug in infinity, we get 1 divided by infinity, so it basically goes to 0. And if we plug in the 1, we get 1 over square root of 2. And so our result there is 1 over square root of 2. Now, the actual value here is not important. The main thing is this a finite number or is this infinite? Because if it's finite, then we know this converges. If this were infinity, we would know it diverges. And so since the value of the integral converges, we can say the series itself also converges by the integral test. moving ahead. Now, these problems, 4 through 10, there's not any particular order here. We just want to determine whether each series converges or diverges. We do want to also make sure we indicate the test that is being used, and then apply that test properly, of course. Now, there's going to be some questions where more than one test is an option. I will demonstrate what I feel is the best test in the given scenarios, but by no means is not the only way to do it. But in some cases, we pretty much want to use the one that we indicate, because there's other that are possible. Like number 5 there, we could do a what could we do there? The real answer to number 5 is going to be a nth term test, because the limit of that thing is not 0 at infinity. But we could do that with ratio, probably. No, ratio is inconclusive. Ratio would give us a 1. I don't know, but the point is that there's going to be some where there's multiple options, but there's definitely a better option in all these cases. First one, though, this is a p-series, because we have 1 over n to the p. Okay. In this case, and we have to be careful how we interpret this, this is n to the 4/3. Because if we interpret that backwards, then we get a number that is smaller than 1 rather than a number that is larger than 1. And that's actually the requirement that we have to check for p-series. If this exponent is bigger than 1, we know it converges. And so that is our conclusion. Since p is greater than 1. Okay. If it were less than or equal to 1, it would diverge, and then that would give us a different outcome. So 5. Probably the easiest way here is looking at the two terms. They actually have the same exponent top and bottom. So I'm going to say nth term test. We might look at that and think limit comparison. And I guess that would work. I don't know, it'd be kind of weird. It would probably work, but it's just going to be so much easier if we do the nth term test. And the nth term test says we can take a limit as n goes to infinity of the expression inside of our summation, minus 3. And since this is not equal to 0, we got a 1 over 2, then we can conclude that it diverges by that nth term test. Okay. Now again, the nth term test, as we mentioned this on the kind of that table of convergence and divergence formulas I gave out on the extra credit assignment. This can only be used to show divergence. So if this is equal to 0, that is not telling us anything. And I see way too many students use nth term tests for things that they should not be using it for. This can only be used if this limit is equal to something besides 0, and only then does it tell us it diverges. So we do want to be very careful about that. Okay. Now, in 6, looking at this, the first thing I notice is that it's raised to the nth power. And the fact that it's raised to the nth power tells us, well, we should try to use an nth root test, the root test specifically. Because in the root test, we take the nth root of a sub n, which is the expression inside here. And that's basically saying we take the nth root of something that is to the nth power, then that root and that power cancel out, and we're just left with 2n minus 1 over n plus 2. Okay. Now, further, the root test says, well, let's just take the limit of this thing. If the limit is bigger than 1, it diverges, and if the limit is smaller than 1, it converges. So we like limit n goes to infinity of 2n minus 1 over n plus 2. So we know this is infinity over infinity, but L'Hopital's rule, we could apply that if we want to, or we can just use the fact that we have the same exponent on top and bottom, so we know the coefficients is going to be the limit. The ratio of the coefficients is the limit. So that's going to be 2 over 1, which is 2, and that's bigger than 1, so it diverges by the root test. Okay, so remember we call this L, and because L is bigger than 1, we know it diverges. Okay. Now 7 we see is similar to number 5 in that we have a ratio of polynomials being divided. But this one is, when we see this particular arrangement where the top exponent is less than the bottom exponent, then it makes more sense now to use the limit comparison test. So we're using LCT for this one. And as far as what we're going to compare this to, that's going to be based on these leading terms. So we're going to let b sub n equal n squared over n to the 5th, which reduces to 1 over n cubed. Okay. Now, this is our original series a sub n, and then b sub n is our comparison series. And we choose b sub n carefully so that it's similar in format to a sub n, but it cuts out all the extra stuff that we don't need. So we eliminate these additional terms that do not have as much of a bearing on the outcome and just focus on the lead terms. And we see that the ratio between those two terms is 1 over n cubed. Now, this specifically is a p-series. P is equal to 3, which means it converges. Because our p-value is greater than 1. So by comparing our series to a convergent series, the suspicion then is that this series itself also converges. But we still have to make sure we follow through with the limit comparison test. So for the limit comparison test, we have to show that the limit as n goes to infinity of a sub n over b sub n is finite and positive to verify that the comparison test actually works. Okay. So, a sub n, that's our original expression. So we'll take n squared plus 3n plus 7 over n to the 5th minus 2n plus 13. Now, we would divide by b sub n, but instead of dividing by 1 over n cubed, we'll multiply by its reciprocal. So distributing that n cubed in the numerator, that's n to the 5 plus 3n to the 4 plus 7n cubed. And we just rewrite the denominator, we're just multiplying by 1 there. And so we need to find the limit of this expression. Now once again, we know it's infinity over infinity. And we could apply L'Hopital's rule 5 times, but at the end of the day, when we see n to the fifth over n to the fifth, we know with the same exponent top and bottom, the limit's basically going to be the coefficients, which is 1 over 1. So our limit is 1. Okay? And the fact that since the limit is finite and positive, okay, that means that our comparison test works. LCT works. But now we have to decide, okay, if it worked, what does it tell us? Well, it tells us that A sub n and B sub n have the same behavior. So because we said B sub n converges, A sub n is going to have that same result. So A sub n will also converge. So if we had selected a function for B sub n, and it turned out that that function diverged, and we verified that the LCT works, then the original series will also diverge in that case. Whatever we have here and here, as long as our test works, these two should be the same thing. So we pick something we know here. We know 1 over n cubed is a convergent p-series. Therefore, we can draw that same conclusion for our original series based on this comparison test. It's a little bit complicated to use. We want to make sure we get all those details in there, though, because that is really what makes this a good approach, is we do need to make sure we get these details here, like I'm showing you. Okay. For number 8, we have negative 1 to the n over 2n plus 1 in the denominator, and it's from 1 to infinity. Now, this is an alternating series. We know it's alternating because there is a negative 1 to the n term. There's a few other alternating terms that we saw, but I'm not going to try to make this confusing at all. It'll just be something like that, negative 1 to a power. So, in our alternating series test, AST, there's two things we have to check. One, we want the limit as n goes to infinity of a sub n is equal to 0, and we want to check if that's true. Well, if we take the limit as n goes to infinity, and I guess I should state absolute value of a sub n in this case, essentially, absolute value is probably not a good way to say that. Probably it's better to say a sub n is the part that's not alternating. So if we just leave out the alternating term, then the rest of that's a sub n, which is 1 over 2n plus 1 in this case. And we see that if we plug in approaching infinity, we get 1 over infinity, so it is going to go to 0. So that's the first thing. The second requirement is that it is decreasing. And the way that we confirmed that it was decreasing is to show that its derivative is going to be negative for the n equals 1 to infinity in this case. So we know an is 1 over 2n plus 1, which we can express as 2n plus 1 to the minus 1. And now we just want to find its derivative based on n. So its derivative is negative 2n plus 1 to the negative 2. And again, it's a chain rule, so we take the derivative inside, which is 2, and then multiply by that. So that gives us a negative 2 over 2n plus 1 in parentheses squared. So I just took this term and moved it to the denominator. We have the negative and the 2 that are still in the numerator. Now, the question is this decreasing? Is this negative? Decreasing means a prime is less than 0. Okay. Well, the numerator is negative, and the denominator, if it's something being squared, that will always be a positive number. So negative divided by positive, we know, is negative. So it meets both conditions. And because it meets both of those conditions, we can say it converges by the alternating series test. Now, if it failed to meet either one of those two conditions, then we would say it diverges. So that's really the question is, one, we have to remember these two conditions that it has to meet, and then one at a time, check that the limit is 0, and then check that it is decreasing. Both of them are true, therefore it converges by our alternating series test. Okay, number 9. We have the sum n equals 0 to infinity of 28 over 3 to the n. Now, there's a couple of ways to look at this, but probably the easiest way, because I've seen people do root test here, but the easiest way, I think, is going to be geometric. It is geometric. It's just a little bit disguised. Okay. So we can look at this and say, okay, we can factor out the 28. Times n equals 0 to infinity of 1 over 3 to the n, which is really the same thing as saying 28 times the sum n equals 0 to infinity of 1/3 to the n. Okay. 1 on the numerator is basically 1 to the n, because we know 1 to a power is still 1. And so by changing it from this to this, we're essentially saying the numerator is 1 to the n. We can just combine that as a single term, which we can do. Okay. So this is probably a clearer picture of what's happening now, and we can see, okay, well, r equals 1/3, and as we said back on problem 2, if the absolute value of r is less than 1, then it converges. And that is precisely what happens here. Okay. Hopefully this will be a really easy problem when we see it. This one and the p-series for sure. And nth term is not that bad. Those three hopefully go very quickly, and it shortens overall the test. And the test is pretty lengthy. I mean, the review itself is 16 questions. I might cut that down to 14 or so, but and I might have already told you by the time y'all see this recording. So, but I think I do cut that down a bit on the actual exam, so that should be helpful. Anyway, number 10. Now, anytime we see all this kind of assortment of terms together, we have a factorial, we have an exponential, we have a polynomial. This just tells us ratio test. That's really the only thing we can do here is ratio test. So a sub n is n factorial over 3n times 2 to the n. And an plus 1 will be n plus 1 factorial over 3 times n plus 1 times 2 to the n plus 1. And in our ratio test, we want to take the limit as n goes to infinity of an plus 1 divided by an. So starting with an plus 1 first, that's n plus 1 factorial over 3 times n plus 1 times 2 to the n plus 1 times, and instead of dividing by a sub n, we'll multiply it by its reciprocal. So that's 3n times 2 to the n over n factorial. So we want to reduce this, and it turns out we can reduce quite a lot here. The factorials, n plus 1 factorial over n factorial, is just going to be n plus 1 on the numerator specifically. If we have 2n over 2n plus 1, then that's just going to leave us with an extra 2 on the denominator, because these n 2's cancel out these n 2's, and there's one extra on the bottom that's unaccounted for. So we still have a 1/2. We can also think of it as subtraction. N minus n plus 1 is 2 to the negative 1, which is 1/2. So however we get that, we should get a 1/2 out of that, basically. We can also see that our 3 is going to cancel. 3 and 3. And those cancel directly, so we don't have to even worry about that. But now, looking at what we still have in our limit, on our numerator, we still have an n plus 1, and we still have that n. The 2 to the n now is gone because of that simplifying that's happened. So we have n plus 1 and n, and on the bottom we have an n plus 1 and a 2. So n plus 1's still cancel out. I feel like this problem was on our extra credit. Anyway, this were very similar to it was on our extra credit already. But we end up with a limit of n over 2, and unfortunately this goes to infinity, which is now bigger than 1, and because we got our limit here bigger than 1, then that tells us that according to the ratio test this will diverge. Alright, so that gets us through those first 6 sections, and like these problems, like I said, 4 through 10, as well as number 3. We already saw some very similar ones to these on our extra credit assignment, hopefully, that we're already making a good deal of sense. But now we get to our problems starting from 11. Now we're talking about the things we've said since then, which is these other 4 sections from this end of the second half of the chapter, basically. Okay, so 11, find a Taylor polynomial for f of x centered at c equals 2 using n equals 4. Now, main thing to remember for Taylor polynomials is the formula that we have. The nth term is going to be the nth derivative of f evaluated at c times x minus c to the n over n factorial. This is true not just for the Taylor polynomial, but also the Taylor series. Okay, that's why it's important we memorize this. Now, for n equals 4, that means we need to go out to the 4th derivative. So that's as far as we go with this. So we need to find f of x, f prime of x, f double prime x, f triple prime x, and f 4th derivative of x. Okay. Now in this case, our function is e to the 2x minus 4. So if we take that derivative, we get 2 times e to the 2x minus 4. Second derivative is 4, e to the 2x minus 4. Third derivative is now 8 times e to the 2x minus 4. And the 4th derivative is 16 times e to the 2x minus 4. Now, we want to plug in our center c, because we said over here in our formula we want the nth derivative evaluated at c. And so that's for everything from n equals 0 up to 4 in this case. Essentially, we're just looking at the first 5 terms of the Taylor series for this function. That's really all it is. When we look at a Taylor polynomial, it's just the first n terms of the Taylor series. But it's a little hard to explain that when we first look at this in 9.7, and then now also having seen section 9.10, we can add that in that bit of context. But anyway, so we want to evaluate these at c, but if we plug in x equals 2, that's 2 times 2 minus 4 in the exponent, so it's just e to the 0. So f of 0 is 1. F prime of 0 will be 2 times 1, so 2. Then we'll get 4, 8, and 16. Those are all 2's, not 0's, I'm sorry. I'm going to use this as the key that I scan and upload, so I'm trying to make sure this is correct. So I apologize for this. It takes a little bit longer. Okay, that's our values, and so those are now these values that we'll use here. So p sub n of x, we're going to have f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared over 2 factorial plus third derivative at 2 times x minus 2 to the third over 3 factorial, and then the fourth derivative at x equals, or at c equals 2 times x minus 2 to the 4 over 4 factorial. Once again, I feel like we need a little more space here. Anyway, we plug in the values that we got. We got 1, 2, 4, 8, and 16 for these coefficient values, and then we can reduce that with our denominators in these three terms, specifically. So P4 instead of n. And I should have said 4 up there, but that's okay. So 1 plus 2 times x minus 2 plus 4 over 2 times x minus 2 squared plus 8 over 6 factorial, or 3 factorial is 6 times x minus 2 cubed, and then 16 over 24 times x minus 2 to the fourth. So putting it all together right here, so we're going to get 1 plus 2 times x minus 2 plus 2 times x minus 2 squared plus 4/3 times x minus 2 cubed and 2/3 times x minus 2 to the fourth. Okay, and so there's our resulting polynomial, fourth degree polynomial at c equals 2. All right, and then in part B, test the accuracy of the polynomial by finding the value of P4 of 2.5 and comparing it to the actual value of e to the first. Okay, now if we plug in P4 of 2.5, and that's 1 plus, now if we plug in 2.5 minus 2, that's going to be 2 times 0.5 plus 2 times 0.5 squared plus 4/3 times 0.5 to the third and plus 2/3 times 0.5 to the fourth. And at this point, we'll just use our calculator to work this out. Let's see. Some of these values are easy. Like this is a quarter, times 2 is a half, this is a 1, and this is a 1. So we have 2.5 already. So 2.5 plus, and we want 0.5 to the third times 4/3. I believe is 1/6. 0.5 to the third times 4 divided by 3. Yeah, it's 1/6. So it's 1 plus 1 plus 1/2 plus 1/6. And then 0.5 to the 4 times 2 divided by 3. What is that? It's 1/24, I believe. Yeah. And so if we put that all together, we get 2.708, and then the 3 is repeating. Okay. And we compare that with the actual value E. And the actual value of E is 2.71828. And so we got pretty close. I mean, we're only off by about 1/100th of a point. 0.01 is about our margin of error here. It's actually a little bit less than 0.01. Looking at these two, so if we were to subtract them, that's more or less what we would have. But yeah, a little bit less than 0.01. So yeah, fairly accurate, even with just a 4th degree Taylor polynomial. But again, it should be most accurate near the center. And our center was 2, and we used a value of 2.5. So we weren't that far away from our center. So. All right, 12 and 13 test or find the radius of convergence of the power series. Now, a radius of convergence, we have to use the ratio test for power series. So we said, okay, u sub n, that's x to the n over n plus 1 factorial, and un plus 1 will be x to the n plus 1 over n plus 2 factorial. And so we want to find where the limit as n goes to infinity of the absolute value of un plus 1 divided by un. So we'll plug in those two expressions. We want to know where this is less than 1. The absolute value of that is less than 1. Now, we know we can reduce the x's, and we can reduce the factorials. So x to the n plus 1 over x to the n is just going to give us a single x, subtracting the exponents. And n plus 1 factorial over n plus 2 factorial is just going to give us 1 over n plus 2. Okay. So we end up with, our absolute value of x we can factor out, but we still have 1 over n plus 2 inside. We want that to be less than 1. Now we can take out the x because when we got this x over here, okay, technically we would put x over n plus 2, but because x is not affected by n going to infinity, we can factor it out. And if we're just talking about n, we don't need to worry about n being positive or negative because we know n is already non-negative. Okay, going from 0 to infinity. Now if we let n approach infinity, that turns out to be 0 in this case. So we're left with the statement of 0 less than 1, which is true for all real numbers. Okay. And so however we want to express that is fine, but our radius of convergence is basically all real numbers. It works for any value of x that we choose. And that's because this is basically an exponential equation we're looking at here. Okay. 13 is the same question, but a different expression inside as we would expect. So we have negative 1 to the n, x minus 3 to the n, and then n times 2 to the n on the bottom. Now, we don't have to worry about the alternating term because we do take the absolute value here. So if we take the absolute value of u sub n, then that is x minus 3 to the n over n times 2 to the n. And if we want un plus 1, then we'll just change each of our n's to n plus 1. Okay. So we have un plus 1 and we have un. So we want to take the limit as n goes to infinity of un plus 1 over un. Inside the absolute value. So we'll have x minus 3 to the n plus 1 over n plus 1 times 2 to the n plus 1 times, and we'll multiply by the reciprocal of u sub n. So n times 2 to the n over x minus 3 to the n. Now again, we can reduce our x minus 3's because we have n plus 1 of them here and n of them here. So there's just one extra on the numerator, which should always be the case. And then 2 to the n, that reduces as well. 2 to the n over 2 to the n plus 1 leaves an extra 2 on the denominator. And then the n and the n plus 1, those are polynomial terms. Those don't go anywhere. So we can take, we have one extra x minus 3 in the numerator. We got that. Bring it outside. Still has the absolute value. We know there's an n in the numerator, and then there's a 2 times n plus 1 on the denominator. Okay. Less than 1. So we have the absolute value of x minus 3 times the limit as n goes to infinity of n over 2n plus 2. And now we look at the limit of that expression. Again, the exponents are the same on top and bottom, so we can take their coefficients as the limit. So that's just going to be 1/2. So our limit is going to be 1/2. So we're going to end up with x minus 3 over 2, absolute value is less than 1. And so now we just want to kind of unfold it from there to get the what we call a compound inequality that represents this radius of convergence. So we would say from there, negative 1 is less than x minus 3 over 2 is less than 1. We can multiply each part here by 2. So that gives us negative 2 is less than x minus 3, This less than 2. And then we'll just add 3 to each part here to get rid of this plus 3 in the middle. And so that gives us actually a positive 1. Is less than x is less than 5. And so there's our radius or convergence or interval over convergence, however we want to specify. Okay. Number 14, this is from section 9.9. 13 was 9, 12 and 13 were 9.8. 14 is from 9.9. Find a power series centered at c equals 1 for the following function. Now, if it's going to be centered at c equals 1, then we need this to be x minus c right here. Okay. It turns out if we know, if we have 1 over 1 minus x minus c, then this is the power series of x minus c to the n. Okay. And that is based on the geometric series, to be honest. But now we're relating it to a geometric power series, I guess we could call it. But by changing this, so now it's a minus x minus 1. Now remember, this negative distributes, so it's minus x and plus 1. So whatever is here, plus 1 has to equal that too. So our conclusion is that's a 1 right there. Okay. If we resimplify this, it should still be equivalent to this expression. So this is 1 minus a negative 1, so it'll go back to being 2 minus x. So the difficult part now is going this direction that we're trying to do, making sure we can set this up that our numbers match. Okay, now the 5 we can factor out, so it's 1 over 1 minus x minus 1, and that matches what we're seeing over here. So now we can just change this directly to a series n equals 0 to infinity of x minus 1 to the n. And so that will be our solution. Remember that if this is a plus, then that it means there's a negative 1 to the n that's present. And even if there's like an extra fraction here, like x minus 1 over 2, it'll be x minus 1 over 2 to the n. So it's just whatever's here is raised to the nth power here, once we get done simplifying. Okay. 15, find a Taylor series representation of the function centered at, and I said a equals 1 for some reason. It should really be a c equals 1, since that's the letter we should be using. I don't know why I mistyped that, but anyway. But yeah, we're using a center of 1, essentially. And so this is from now section 9.10. We have f of x is natural log of 2 minus x. Now, we know our Taylor series is going to be the sum n equals 0 to infinity of the nth derivative of f evaluated at c times x minus c to the n over n factorial. So we have to know that formula. And this is actually the same expression we talked about in that previous, I think it was 11. Yeah, problem 11. That was the nth term for the Taylor polynomial. We're seeing the exact same expression right here. Okay. So that's what we're working with. Now, x minus, okay, we know c is 1, so we're going to have the sum n equals 0 to infinity of the nth derivative evaluated at 1 times x minus 1 to the n over n factorial. Now, having set up that, the only thing we really need to find now is the formula for the nth derivative of this function, and then we'll plug in 1 and see what that gives us. So let's look at our function. We have f of x equals natural log of 2 minus x. This is a little confusing, but when we differentiate this, remember that for the first derivative, whatever is inside the logarithm goes on the denominator, and then the derivative of this term goes on the numerator. So it's actually negative 1 over 2 minus x, or negative 2 minus x to the negative 1. And again, it's going to be nicer in this form because we can use the, it's probably easier to use the chain rule than it is to use the quotient rule, I guess I would say. So let's look at the second derivative. Well, we multiply by the negative 1, which will make it positive 2 minus x to the negative 2, but then the derivative inside the parentheses is negative 1, so it's negative 2 minus x to the minus 2. Third derivative, we multiply by the negative 2, that makes it a positive 2, times 2 minus x to the negative 3, times derivative inside the parentheses is negative 1. So it makes negative 2 times 2 minus x to the negative 3. And then let's look at the fourth derivative. We multiply by the negative 3. That changes it to a positive 6. 2 minus x to the negative 4 times negative 1, the derivative inside the parentheses. So negative 6 times 2 minus x to the negative 4. So now we have to generalize this for the nth derivative. Okay. Now, what we notice is, well, first of all, our original function probably isn't going to be part of our pattern. Our pattern, we can see a pattern emerging with these derivatives, 1, 2, 3, 4 derivatives, doesn't really fit our original function. But that's okay, because what is natural log of 2 minus 1? Well, that's natural log of 1, which is 0. So the original function is actually equal to 0 at the center c equals 1. So we don't need to start our series at n equals 0, because the first term of the series is 0, so we'll just start at n equals 1 instead. But now let's find a pattern for n equals 1 or more. So for our first, all of our derivatives are negative. That's the first thing we notice. So there's going to be a negative sign here. Now, in front of that, there's a 1, a 1, a 2, and a 6. Now, we can see that we're multiplying by an increasing value at each step. We're multiplying by negative 1 in that derivative, times negative 2, times negative 3, and then times negative 4, and so on. So we are getting a factorial in that coefficient expression. But now notice that 6 is only 3 factorial, but this is for the fourth derivative. The third derivative has a 2 factorial. Second derivative has a 1 factorial. First derivative has a 0 factorial, which is still 1. So this is actually n minus 1 factorial that we've got there. And then we see 2 minus x appears, and then the exponent on that term is now the same as the number of derivatives that we've been taking, except it's negative. So we'll say that, okay, 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4. So for the nth derivative, we expect it to be negative n. And now, if we plug in x equals 1, our center to this nth derivative, then we're going to get negative n minus 1 factorial. 1 to any power is just going to be 1. Okay. So this expression now we can come back in here and resubstitute. So f of x will equal the sum, n equals 1 to infinity. Now, notice we changed it from n equals 0 to n equals 1 because our original function value was equal to 0. So we just peel off that first term and start at n equals 1 instead. And then we plug this in, negative n minus 1 factorial, where fn of 1 goes. That's what we just found. And then just fill in the rest of this. So it's negative n minus 1 factorial x minus 1 to the n over n factorial. But now, because we're dealing with these factorials, we know we can reduce those still. N minus 1 factorial over n factorial is just going to be 1 over n. It's just going to leave an n on the denominator in this case. So, as we simplify that, we get sum n equals 1 to infinity of negative x minus 1 to the n over n. And so that is our Taylor series for this particular function, natural log of 2 minus x centered at 1. Okay. Now, this last problem, 16, we want to approximate the value of the integral using an appropriate power series, I guess I should say. And we'll do that by looking at the first. Now, this time I specify using the first 3 terms of the resulting series because this one, what I've found is that it does take a long time to gain any level of accuracy. So we have an approximate value. It turns out we can solve this problem by actually doing substitution. There's actual methods we can use to find this integral. But rather than worrying about that here, I just went ahead and say, okay, we know what the approximate value is, so we can at least compare our answer. We should be close. It may not be great, but we should be fairly close at least. But just use the first 3 terms of the resulting series as an alternative to getting a desired level of accuracy. Because it turns out for this function, it's going to take a while. So we start with the hint here is that we start with the power series for 1 over 1 plus x, which is 1 over 1 plus x is equal to the sum n equals 0 to infinity negative 1 to the n times x to the n. Okay, just an alternating geometric power series. Now, what happens if we change this to an x to the 6th in the denominator? Well, if we change that to x to the 6th, then that'll be negative 1 to the n times x to the 6th to the n, which is negative 1 to the n times x to the 6th n. Okay? And the other thing is, well, what if we then also multiply by x squared in the numerator? Okay. And so that is x squared times the previous result, because all we're doing now is multiplying by x squared in the numerator. In our previous result, we got negative 1 to the n times x to the 6th n. And if we bring our x's in together, we have x squared times x to the 6th n that means we're going to have the sum n equals 0 to infinity, negative 1 to the n, x to the 6n plus 2. Because if we're multiplying these two terms, we're adding their exponents. Okay. So, this is the function we actually want to integrate. Therefore, we can now integrate this series. So the sum n equals 0 to infinity, negative 1 to the n, x to the 6n plus 2 dx. Okay. And so the integration for that, we're going to have the sum n equals 0 to infinity, negative 1 to the n, x to the 6n plus 3 over 6n plus 3, and that's from 0 to 0.7. Now, we know that if we plug in 0 for x, that's just going to zero out the whole thing. Okay. So now we really just have to plug in the 0.7. So the sum n equals 0 to infinity of negative 1 to the n times 0.7 to the 6n plus 3 over 6n plus 3 minus 0. And now we just want to look at the first three terms of this series. Now the first three terms means n equals 0, n equals 1, and n equals 2. So first three terms starting from this point. So n equals 0, if we plug that in, negative 1 to the 0 is positive 1. 6 times 0 plus 3 is 3, so we have 0.7 to the 3 over 3. Okay. For n equals 1, negative 1 to the first power is negative 1, so it's negative. 6 times 1 plus 3 is 9, so we have 0.7 to the 9 over 9. And then n equals 2. Negative 1 squared will be a positive 1, so plus 6 times 2 plus 3 makes 15. So we have 0.7 to the 15 divided by 15. And so now we just want to approximate that on our calculator. So we get 0.7 to the third divided by 3 plus, parentheses, not plus, I'm sorry, minus. Okay, so minus, parentheses, 0.7 raised to the ninth divided by 9. And then plus, parentheses, 0.7 raised to the 15 divided by 15, close parentheses. And so for this one, we get 0.110166103. Now, compare that to the actual answer. We actually got a pretty good amount of accuracy. And I didn't write down the individual results here because we didn't want a specific level of accuracy. But if we look at these numbers, 0.7 cubed divided by 3, and this is 0.114333. I'll just go 6 places. 0.7 to the 9 divided by 9 is 0.004484. Okay, and if we get 0.7 to the 15th divided by 15, we actually get 3 places of accuracy here. Okay. Because we get 3 leading decimals at that term. So if instead of saying just use the first 3 terms of this resulting series, I could have said keep going until we know we're accurate to at least 3 decimal places. Well, 3 leading zeros means this will be accurate to 3 decimal places. And if we just combine those together, it should be pretty close to what I wrote, but just to be a little bit more specific here. Yeah, it is the same thing as what I wrote, at least up to that point. I might just, for clarity's sake, get rid of all this, so that when I give that to you later, it won't be weird. Okay. But yeah, it's pretty close to our actual answer. We know it's actually accurate to 3 decimal places, and it turns out the next place, it's also accurate to the 4th decimal place, even though we don't see that necessarily, because our number was 0.11014. So our margin of error is only in that 5th place after the decimal. All right, that wraps up the review. But if you do have any questions or anything, be sure to message me. I hope this was helpful. Anyway, best of luck studying. Let me know if you need anything. Have a good day.